It's 11:11. I wish I had a physics tutor. I don't understand anything on this gravitation test tomorrow. Please, God, I wish for a physics tutor. Who are you?
Well, hi. I'm your new physics tutor, Mrs. MacDonald. Today, I'm going to teach you about doggone gravitation so you can ace this test.
Miss MacDonald? What is doggone gravitation?
Now listen a minute, partner. Gravitation, we're going to leave out the doggone part. Gravitation is the movement or tendency to move toward a center of attractive force, as in the falling of bodies to the earth.
So what formula do we use for this gravitation thing?
Now Leila, there's not just one formula for gravitation. There's quite a few. First of all, we have T equals 2 pi root r cubed over GME. GME, gravitational constant, mass of Earth. See what I'm saying? Next we have V equals dm over r squared. That's velocity equals gravitational constant over r squared. Radius. Duh.
Wow!
Then we have G equals gm over r squared. You're getting my drift right now, right?
Yeah.
Now we have Ti over T2 squared equals Ri over R2. That one's starting for a loop, don't we? Next we have Fg equals G times M1, M2 over R squared.
So how do I know which equation to use?
Leila, it depends what planet you're on, because on different planets, we have different masses. So your teacher in the question is going to give you which variables you have. According to the variables you have, you take them, plug them in.
What?
For calculating distance from the sun, and to compare distance in periods from the moon to the artificial satellites orbiting Earth.
Can you do an example problem?
Well, of course, darling. Let's start with example problem 1. Mars has a mass of about 6.4 times 10 to the 23 kilograms, and its moon, Phobos, has a mass of about 9.6 times 10 to the 15 kilograms. If the magnitude of the gravitational force between the two bodies is 4.6 times 10 to the 15 newtons, how far apart are Mars and Phobos? That works the problem. Under our givens, we got the mass of Mars, which is 6.4 times 10 to the 23 kilograms. The mass of Phobos, which is 9.6 times 10 to the 15 kilograms. And then we got F of G, which is the force of gravity. 4.6 times 10 to the 15 newtons. And then we have G. 6.67 times 10 to the negative 11 newton meters squared over kilogram squared. And for our unknown, we have R, which is radius, I think. And for E, we have F of G equals G, M1, M2, over R squared. So why do we use this formula, one may ask? We have F of G, two masses, we don't have R, but that's what our unknowns for. But we have all the rest. We have all the meat and potatoes, but this, right here. So we're going to come over and solve. So basically, all we did was we plugged and chugged. 9.46 times 10 to the negative 6 meters for your radius.
Thanks, Miss MacDonald. I finally understand.
Wow, wait a second, darling. We ain't done yet. Let's get a little bit more in depth with this man named Kepler. He was a German scientist who studied Brahe's ideas and was convinced that geometry and math could be used to explain the number, distance, and motion of the planets. The first law states that the paths of planets are ellipses with the sun, I won't focus. Second explains that an imaginary line from the sun to a planet sweeps at equal areas in equal time intervals. The third law states that the square of the ratio of the periods of any planets revolving about the sun is equal to the cube of the average distances from the sun.
Awesome. What equations do we use?
What we use is T1 over T2 squared. So, for example, the moon has a period of 27.3 days and a mean distance of 3.9 times 10 to the 5 kilograms from the center of the Earth. Use Kepler's laws to find the period of a satellite in orbit, 6.7 times 10 to the third kilometers. So basically, this is our work. We have all the givens. Our unknown is the period of the satellite. Our equation is, like I stated, T1 over T2 squared equals R1 over R2 squared. So, T of satellite, T of moon, over radius of satellite, over radius of moon. So to solve it, we just plug and chug as usual. The square root of TS squared, that's going to get rid of that square. And then we're going to square root this right here, which we got from this portion of our equation. So that means our period of the satellite is 0.061 day.
Wow, so many formulas. Any more I need to know?
Two more involving gravitation. The next one involves the period of a planet orbiting the sun. It's this one. The period equals 2 pi root radius cubed over GM mass of the sun. Mass of the sun. So for this one, we're going to use the planet Mercury travels around the sun with a mean orbital radius of 5.8 times 10 to the 10th meters. The mass of the sun is 1.99 times 10 to the 30th kilograms. Determine how long it takes Mercury to orbit the sun in Earth days. So we have our givens here, as y'all can see. So our unknown is the period of Mercury, and our equation is, as you guys saw, T equals 2 pi root R cubed over GME. So then, we just plug and chug, as you guys see. We're going to simplify these down into the root. We're going to keep on going. We're going to divide this by this. And we're going to get 88 days. Get a ball.
More formulas go along with gravitation.
Just one more, darling. Hold your horses now. This next problem is in regards to the speed of a satellite orbiting Earth. Velocity equals the root of GME over R. Actually, how about you show us a problem on the board, Miss Leila?
I mean, yeah, I'll try. Alright, Miss McDonald, did I do it right?
Yes. Get it, Bob.
Okay, so the problem reads, assume a satellite orbits Earth 225 kilometers above its surface. Given that the mass of Earth is 5.97 times 10 to the 24th kilograms and the radius is 6.38 times 10 to the 6 meters, what is the satellite's orbital speed? Okay, so I put the radius of the satellite, and I got 2.25 times 10 to the 3rd meters, and then the radius of the Earth, which is 6.38 times 10 to the 6 meters, and you have to add those together to get the radius, and you get 6.61 times 10 to the 6 meters, and then the mass of the Earth is 5.97 times 10 to the 24th kilograms, which is given in the problem, and then gravitation. Your unknown is velocity because it's asking for the speed. You plug it into this equation that Miss McDonald just gave us. Plug, and you get 7.6 times 10 to the 30th. Yes, I finally get gravitation. This is the best day ever.
Looks like my time's here is done. Bippity boppity boo.